Now we take a look at integration of vector functions. And again, the integral of a vector function is exactly what you think it is. You just take the integral of each component. And as we'd expect, the variable is going to be the parameter. So suppose we have a vector function, r of t equals 6t, comma, cos t, comma, e to the t. Let's integrate that. So I can just write down the answer, but let me also introduce the notation. It's going to be the integral of the r vector t dt equals, and in the first component, we're going to have 3t squared, and it's going to be plus a constant. And then the second one is going to be sine t, also plus a constant. And then the third one is going to be e to the t plus a constant. Now each of those does not need to be the same constant. So we're simply going to indicate that with C1, C2, C3. And there's the final answer. Another way to write this is to put the indefinite integral as one vector, and then to say we're adding on not a constant, but some constant vector. That looks a little bit more like the single variable calculus version. So notation, which we kind of already got to look at, is that we can write the integral of r of t as the integral from a to b if we have boundaries of r of t dt, or it's the integral from a to b with the bold r. Okay. And we also have a fundamental theorem of calculus for vector functions. And again, it's just the fundamental theorem of calculus applied to each component. So we have it like that. The integral from a to b of r prime of t dt is just r of b minus r of a. So let's apply all that to a problem, and in this case, it'll be an application. So let's take a look. So a particle has acceleration vector function a equals 2, 3t, e to the t. And now we know that at t equals 0, its velocity is 1, 0, 0, and we know that its position at t equals 0 is 2, 3, 1. So let's find the position vector function. So what do we do? Well, we've got the acceleration vector to start. So where can we go from there? We know that because the position vector, the derivative of position is velocity, derivative of velocity is acceleration. Therefore, since we're starting with the acceleration, we can take the integral. So we know that the velocity vector is just the integral of the acceleration vector dt. So that's the integral of 2, 3t e to the t, all of that dt, which is just 2t plus constant c1, and then 3 has t squared plus constant c2, and e to the t plus some constant c3. Next, we can use the condition that we know, which is that velocity at 0, we know, is 1, 0, 0. And that's got to be equal to 2t, so plugging in 0 plus c1, 3 halves 0 squared plus c2, e to the 0 plus c3. And that gives us that 1, 0, 0 must equal c1, c2, and 1 plus c3. So put it all together, we now know the constants are 1, 0, and negative 1. So finally, that lets us say the velocity vector function is 2t plus 1, 3/2 t squared, and e to the t, e to the t minus 1. And that is the velocity vector function. Next, we can do it all again in order to find the position vector function. So let's do it all again. So we know that r equals position vector equals the integral of the velocity vector. So that's the integral of the vector function we just found, 2t plus 1, 3/2 t squared, e to the t minus 1, all of that dt. And that equals t squared plus t plus some constant. I could use c1, c2, c3 again, but I already used them. So I'm just going to say d1, d2, d3. Okay, t squared plus t plus d1, 1/2 t cubed plus d2, e to the t minus t plus d3. And now, again, let's plug in the fact that we know. Let's use the fact that we know in order to figure out what those constants are. We know that r of 0 is 2, 3, 1. And that's got to be equal to 0 squared plus 0 plus d1, 1/2 0 cubed plus d2, and then e to the 0 minus 0 plus d3. So 2, 3, 1 equals, that gives us d1, d2, 1 plus d3. So then the constants are respectively 2, 3, and 0 for d1, d2, d3. So put it all together, and we have our position function, t squared plus t plus 2, 1/2 t cubed plus 3, and e to the t minus t. There you go. And just as in single variable calculus, you have to make sure that you plug this in and solve for the individual constants. You can't just assume that the numbers there, the numbers given in the initial point, are the constants themselves. So that is your basics of how do you do integration of a vector function, and that was our first application from the basic setup of motion with position and velocity and acceleration. Okay. Next, we go on to another application, one that could be familiar from single variable calculus, length. So how do we find length for a vector function? Well, we've seen what the formula is in 2 dimensions for length for a vector function. S is the integral of the square root of dx dt squared plus dy dt squared, all of that dt. And in 3 dimensions, the formula is exactly what you think it is. The length is going to be the integral of the square root of dx dt squared plus dy dt squared plus dz dt squared, and then all of that dt. Now, there's another way to write this formula. Since we know that the derivative of the position vector is just dx dt, dy dt, dz dt, we can rewrite this formula as everything that's being integrated is just the magnitude of the derivative vector. And furthermore, the magnitude of the derivative, since the original vector function is position, its derivative is velocity, and the magnitude of that is the speed. So notice that what the formula for arc length really says is that the total distance traveled is just the integral of speed with respect to time. And you know what? That makes sense. So now we've got our formula, and we know why it makes sense. So now let's go ahead and apply it to a problem. So let's find the length of the helix. Vector r equals sine t cos t t. I'm going to go, t goes from 0 to 2 pi, which is 1 revolution. Remember this helix, we've seen the graph before, it looks like a corkscrew. So let's take a look. So the first thing is we're going to need all the derivatives. So I'm just going to write that down shorthand by noting that we need dr dt. So dr dt is cos t, negative sine t, and 1. So now length s is just going to be the integral from 0 to 2 pi of the magnitude of dr dt, because that is just the speed, and then all that dt. So this is just the integral from 0 to 2 pi of cos t squared plus negative sine t squared plus 1 squared, square root of all of that, dt. And then something really nice happens. That's going to give us a cosine squared plus a sine squared, and that's just 1. So this just winds up being the integral from 0 to 2 pi of rad 2 dt. So altogether this just gives square root of 2 times t, evaluated as t goes from 0 to 2 pi, and that just gives you 2 square root 2 pi. And there's your length. So let's just look at a short summary of some of the things that we've done. We talked about how to take derivatives and now integrals of a vector function. And there's one really important application or important relationship, which is when you have a position function, its derivative is velocity, and the derivative of that is the acceleration. And it also goes vice versa. If you have an acceleration function, when you integrate that, you can get a velocity function, and then the integral of the velocity vector gives you the position vector. And then finally, the magnitude of the velocity vector gives you the speed. And then we also have another nice application for arc length. There's a long formula for it, but the shorthand version is that arc length is just the integral of the speed dt, where the speed is just the magnitude of r prime, the velocity vector. And so that's a look at how we deal with velocity functions and how we take the integral of them, vector functions. Vector functions and how we take the integral of them, and a couple of applications.